In the last video I talked about a generic reaction that I also pointed out could be something written for sulfuric acid. Let's take a look at hydrogen sulfide. Make sure that you know your anion names because this should not be a sulfate or anything. This will be hydrogen sulfide. Now what I'm going to have us do first is we're going to write our stepwise reactions because you can see that we can imagine this having two different pieces. The first time an H plus pops off and the second time one does. Now if we were to do that and write these out, we could determine a K for each of those subreactions. So let's take a look. So we'll have H2S, and we're going to only pop off one of my H pluses so far. We're going to have HS single minus. I'm going to call that portion's equilibrium constant K1. Now we can take this substance and take a look at its equilibrium by writing our second reaction. And you can even see that if we were to combine these two, this and this would cross out. We'll end up having two ions of H+, and so we end up having the exact same reaction that we had written up here. That should always be true. Now, let's go ahead and get our equilibrium constants written for each of these two. I'll write K1 equals, see, so we'll have our products on top, H+, HS minus. Our stoichiometries are 1, so we don't need anything in the powers. And then I'll go ahead and put my reactant on the bottom. And that's how we'd write that equilibrium constant. And I've gone ahead and just written in our next equilibrium constant, because you can see it's the exact same process we had above, and I'm pretty confident that we know how to do that, so just to save us a little time. Now if we were to try to write one for our original reaction, I want you to notice something. I can just go ahead and do our usual as well. So our overall K would equal, and as always, reactants and products. What belongs right here? Remember, our stoichiometry always goes into the power. We saw that in our last video. So we'll have that, we'll have that. On the bottom, we'll have our original reactant, and that would be our K. Now what I want to show us is that if we were to combine these two Ks, we should be able to get this K as well. Because it's still the same physical processes, we should still have the same overall equilibrium. All we're doing is we're looking inside of this K and looking at the stepwise pieces. So if you're given a couple of reactions, you'll see that this is going to be very consistent. But instead of deriving it, I want us to just take a look at the rule to see if it's consistent. So our rule is actually going to be that K1 times K2 equals our overall equilibrium constant. Let's just go ahead and verify that that really is true. So I'm going to have all of these. Notice if I multiply this times this, I'm going to get H plus times HS minus. I'm going to omit the dots because we know that this is also the shorthand. We're going to have another H plus, and this is coming from K2 now. And more coming from K2, we'll have S2 minus. This is going to be over our H2S. So that's the bottom half of K1. Now we need the bottom half of K2. Get my minus sign in there. You can see this is what everything should look like. But we also need to do a little cross-canceling. And we should probably combine these two terms. And when we do that, we end up having H plus times itself is going to be squared. We're going to have S2 minus. Then we still have our H2S on the bottom. And lo and behold, look at that. we have a consistent result. So hopefully you see this, and that makes it very concrete in your mind that whenever you need to combine two k values from a table to come up with some sort of a specific reaction, that's how you do it. Now, we could do that for multiple pieces. We could have a 5-step reaction, and we can combine all their k's by multiplying them. And that'll give us our total k for the reaction. That's what we do when we're doing something and looking at everything stepwise. But sometimes what we care about is how much the cumulative equilibrium constant has become at each of those steps. In other words, instead of caring about getting to the end product, if what we care about is how much has accumulated in each of the steps, just kind of do it like this. So if we start out with that stuff, making that stuff, and that stuff, and that stuff, and that stuff. If we look at this whole piece, and then we look at this whole piece, and then we look at this whole piece, instead of calling those k's, we're going to call them betas. And that's most important when we're talking about a metal grabbing some ligands. That's the usual spot that you'll see this. And it's toward the end of this chapter. Make sure that you look in the textbook to see an example of that, and make sure that you're comfortable with it, because it's a notation that you will see when we're talking about metal titrations especially, but we won't really focus on doing a lot of metal titrations on the lab portion of our class. That said, it does show up on a lot of the standardized sorts of exams, and it's something you definitely want to have in your knowledge, because metals are an emerging thing. We've been using metals for a long time, but more and more organometallic compounds are something that you're going to be seeing as pharmaceuticals, as reagents, as biological reactants, just lots of different places, so make sure you're comfortable with the notation.